Okay, hi everybody. So we're going to start very quickly with the first speaker. So basically, the way the course is structured is we have two 40-minute talks at the beginning, which are really about the basics. Sorry, three 40-minute talks at the beginning, which are really about the basics of how you can use pattern recognition methods in general, with some emphasis on neuroimaging. And then as the day goes along, it moves a bit more towards specialize what is so special about neuroimaging data and why multivariate predictive models are particularly good for this kind of data. So the first speaker of the session is Anila Rao from UCL, who's going to talk to you about really the essentials of machine learning and pattern recognition.
Okay, thanks, Jonas. So yes, I'm just going to be giving an overview of the sort of principles and tools, some of the basic ideas for when we want to use pattern recognition in neuroimaging, why we use it and why it's helpful. So as an outline, I'm going to firstly sort of go over the pattern recognition framework, and then going to move on to linear models for classification and regression. Then on to kernel methods, which are particular sort of methods that we can use for solving some of these problems. Then talk about how we evaluate our models, of course, very important. And then some examples, some example applications. So the first thing is that we can think about how pattern recognition relates to or compares with sort of mass univariate analysis. So in mass univariate analysis, the typical sort of GLM sort of thing that we'll be doing when analyzing neuroimaging data is that we'll be learning about how to get from a cognitive state or group membership, how this is encoded in patterns in the brain. And this enables us to do things to look at, for example, group differences between, find areas in the brain that, for example, are significantly different between different groups. Pattern recognition analysis, on the other hand, actually does a sort of a decoding step instead. So it takes the brain images and then we can decode and then try and, for example, predict a cognitive state or a group membership. And the main advantage of this is that it can be much more sensitive to detect spatially distributed patterns, for example, because it's multivariate. And secondly, we can get predictions at the single subject level, which of course is very useful. So just to introduce the pattern recognition framework, we have a set of inputs or brain scans. So we think of these here, these are these X1 to X3. And we wouldn't have typically a mathematical model available to take us from the input to the output. But even in the absence of a mathematical model for this, some sort of physical model, what we can do is apply machine learning methodology instead. Now this gives us, these are essentially a group of, there are sets of different sorts of algorithms that can learn a function without needing this sort of prior model of exactly some sort of prior sort of physical or neurological model. So we can use these, and these can take us from, we essentially learn a function during the training phase. So you can see the box with the learning training phase there that takes the training examples, and then we generate a function or classify f that takes us from the inputs, which are the x's, to the outputs, which are the y's. And then this gives us our function f. And then what we can do in our testing phase is that we can apply this to a test example to produce an output or a prediction for our test example. So in neuroimaging, we can apply these sort of techniques as well. So this is just a slide to outline how we would do this in a typical example. So we would have a set of brain scans from a particular task. So if it's sort of neuroscience application, we'd have brain scans from a particular task. Or if it was a clinical application of a particular group, so we'd have one set of brain scans from which we've extracted a feature vector. So X1 here is a feature vector. I'll talk about that what exactly that means in a moment. And we'll have a corresponding label that tells us which task or group the scan is associated with. And we'll have this for example, 2 different tasks or 2 different groups, if that's what we're interested in. And then during the model training phase, we will learn this sort of predictive function, which is the output on the right-hand side, which is often, for classification, it will be a decision boundary that sort of describes where in the input space, how to get from the input space to our label that tells us which task or which group we're associated with. So then when we have a new subject, which is at the bottom of the slides, we've got a brain scan of a new test subject, we'd call it. We'd once again extract its feature vector xi. We have the label, which we don't know what it is, but we've built our model. So during the testing phase, we can just apply this model to our test subject and give us a prediction. So in this case, the classification task, you will have a +1 or a -1 indicating which task or group the subject is, we predict that this subject is part of. So in neuroimaging, we have to firstly extract the features from which we build our models. So there's many different ways we can do this. So it's the most, in a sense, the most obvious way is just to use the whole brain volume. So if we use the whole brain volumes, we can extract the 3D matrix of signals at each voxel. And then once we have that, we just unwrap that into a very long feature vector of the dimension, which will be the number of voxels here, because we're using the whole brain volume to do the learning. Alternatively, we can use a region of interest. So this is useful if we have some sort of prior knowledge. So that's in the bottom half of the slide there. I think that's supposed to be the primary visual cortex. So if we're interested or we had some prior knowledge that this region is going to be important in prediction or somehow it's associated with the clinical groups, we might focus on that particular region and then just once again produce a feature vector, in this case much smaller than using the whole brain volume. So just to introduce the notation, we have our set of examples xi. So these are going to correspond to the feature vectors from our set of subjects. So it'll be like x1, x2, up to xn, which is where n is the number of subjects. So we extract feature vectors for all of these examples, and these feature vectors will be of size 1 by d, where d is the number of voxels in either the whole brain or a region of interest, if that's what we're interested in. Then we'll also have the set of labels y, and these are either categorical values for classification, for example, or a continuous value for a regression. And this is what we're trying to learn. We're trying to learn how to get from the xi, the feature vectors, to the labels, so that we can then apply this to new examples where we don't know what the labels are. So it's good to start off with quite a simple example. So here, we're just working on the slide from top to bottom. We're imagining that we've scanned a subject with a very, very coarse resolution. So we just have 2 voxels, a left and a right hemisphere voxel. Now, as you work down the slide, so then what we've done is we've recorded for 2 different tasks the values in the brain for these 2 voxels. So that's given by the pink versus the blue there. And then we're presented with a new brain volume where we have, once again, the images for those 2. We have the signals for those 2 voxels, and we want to know, well, what is the task that this person was doing at that point in time? So one way of thinking about how we do this in machine learning is to basically plot the one voxel against another. So here it's a bit busy, the slide, I can see, but so we've basically plotted, so we have 2 axes on that graph at the bottom, voxel 1 horizontal and voxel 2 the vertical, and we've basically plotted the voxel intensities for the different tasks. So in pink, we have the task 1, and then we have task 2. And then we might, for example, then in the new subject have another volume which is shown in grey. And then we would try to learn essentially a hyperplane that separates the two classes. So this would be, and there could be many different ones. So here we can see a series of the red lines essentially try to separate the pink and the blue volumes. And as I say, there could be many different choices. And these are all parameterized by a weight vector W and a bias term B. Now in regression, sorry, let me just go back. So what we would, forgot to say that what we'd do, for example, for that new subject in grey, the sort of the new test subject, once we have this line that separates the two different tasks, we would then basically look and see on which side of this boundary does this test subject lie, and if it sort of lies, you can see that it would lie on the same side as the second task. So we would probably predict it as being associated with the second task. So in regression, it's sort of a similar story, but here we've tried to do a sort of the plane, hyperplane represents a fit of the data in terms of the intensities at the voxels. And then what we can do once again to evaluate to get a predicted clinical score, we can once again use the hyperplane and then project and get the predicted clinical scores that you can see. So it's essentially the same idea, because both for regression and classification we've got a linear model here, so they're parameterized in exactly the same way. So as I was saying, so the linear models are parameterized by a weight vector and a bias term. The weight vector W and a bias term B. Now what we can do is that we can write the weight vector as a linear combination of our training examples. So you can see that here we've written W as a linear sum of the training examples xi. The alpha I describe the weights, individual weights of each example in the sum. And once we have that, we can then do predictions for a test example x star by just plugging this in to our predictive function there. So if it's regression, this will give us our prediction score, or if it's classification, it will be the distance to the decision boundary. So how should we really interpret the weight vector? Okay, so we can go back to this simple example where we've just got two voxels. We've done a training, we've got examples from the first class in the top, and then we've got examples from the second class below that. We've done a training, and we've learned this model weight vector that helps us to distinguish between the two classes. And when we have the test example at the bottom with particular values for the voxels, so here I think 1 is 0.5 and 1 is 0.2, we then apply the predictive function by multiplying by the model weight vector. And once we evaluate the predictive function using this model weight vector, it then gives us a score. So in this case, unfortunately, this is so unfortunately you can't quite see the working out there, but all we're doing is just doing the dot product, or the weighted sum of the weight vector and the voxel intensities. And then this gives us a prediction or a predictive score, which is 1.9. And because it's a positive value, we associate this with the first class. So an important point to make here is that in these sort of multivariate models, the predictive function output is a function of all of the voxels or features that we're using. So it's quite dangerous to really look at any one particular weight in any one particular part of the brain in isolation, because the predictive function depends on everything, the sort of the joint vote of all of the voxels altogether. So in neuroimaging, if we want to use pattern recognition, probably the main obstacle is the fact that the dimensionality of the data is much greater than the number of examples. This is called ill conditioning. So this makes learning a hyperplane for regression or classification very difficult. well, to learn one that's reliable is very difficult. So the possible solutions for this, you can use a region of interest. So for example, if you have some prior knowledge about some particular region, use that to reduce your dimensionality. You could use some sort of data-driven feature selection strategy instead, which once again will reduce dimensionality. You could use something called Searchlight, which I think sort of builds local models around in neighborhoods of voxels, again to reduce the dimensionality. And finally, you can use kernel methods and regularization to handle this situation. And these provide really a very powerful framework for investigating data that have, I mean, these methods are used not just in neuroimaging, but in sort of all sorts of applications. Now, kernel, if you want to use kernel methods, what are they? They consist of two different parts. Firstly, we compute something called the kernel matrix. So this maps the data into a feature space, and I'll come on to that in a second. Secondly, we have a learning algorithm that uses the kernel matrix that we can then use to do our predictions. So why would we use a kernel method? Well, for one thing, computationally, they're quite convenient because, as we'll see, they represent a sort of computational shortcut. So even though we're handling very high-dimensional data, we can do our representations in quite a compressed way. Secondly, we can use the dual representation, which is something that I'll also come on to, combined with some regularization. And this allows us to deal with this sort of ill conditioning that we typically see in neuroimage applications. So firstly, describe the kernel matrix. So a kernel is a function that for two patterns, so for us this will be 2 brain scans, returns a real number characterizing their similarity. So there's actually many different choices of kernel that you can use, but probably the most simplest is to just take a dot product between the 2 feature vectors, and that would just be what's known as a linear kernel. So in the example I've got here, you can see this sort of a square, colored square in the bottom. This is the kernel matrix that has been built for a set of examples. So each row and each column indicates the similarity between particular training examples. So in this case, we have the 4th row and the 2nd column is the dot product of the voxel intensities for the 2nd brain scan and the 4th brain scan. So this is an example of a linear kernel, how we build one up. So how do we actually make predictions with kernel methods? Well, we can start off with what I've been talking about, really, which is we just essentially represent the predictive function using a weight vector and a bias term. So that's the first line, and that's what's known as the primal representation. But then, because we know that the weight vector is just a linear combination of the examples, we can then go on to the second line and rewrite it. And we can see here that we've then got this dot product of the training examples and the test examples. But this is just the kernel that we've already just described. So the third line shows, rewrites it in this way, and this is described as the dual representation. And it's this that typically we work with when we're trying to solve these problems in machine learning. Oops, sorry. So we would mostly work with linear kernels, but it's worth saying something about nonlinear kernels as well. In non-linear kernels, you once again take the dot product between 2 feature vectors, but you firstly do a projection. You essentially transform the features into new features first, and then take a dot product. So the first line here, this phi that you see is this operator that transforms the original features into a new set of features, and then you take the dot product. And you might say, well, why bother doing this? the reason is that if we're just using a linear kernel, we might find that we can't actually classify or predict very well. So here's an example here in the original space. So the picture on the left there, you've got two classes. You've got the crosses and the circles, and you want to find a way of differentiating and classifying them between them. But you can see that there's no line that's going to separate the two classes. It's actually this sort of oval shape that you would use to distinguish between the two classes. So what the nonlinear kernel will do will essentially take the original features, project them into a higher dimensional space, into a new feature space on the right. And in that new feature space, you can indeed separate them with a hyperplane. So that's essentially the idea. You sort of generate these sort of new high dimensional features in which you can just apply a linear function for classification or regression. But in practice, we quite rarely use nonlinear kernels in neuroimaging, especially if you're using the whole brain as image features. The reason for this is that the neuroimaging data is already extremely high dimensional, so this already makes it very challenging to find a reliable and robust predictive function. We've also got very small sample sizes. If you're lucky and you've got clinical data, if you've got over 100, you're doing quite well there. So, and this is compared to perhaps, tens or hundreds of thousands of voxels. So to use a linear kernel is actually a far safer option, and so nonlinear kernels don't really bring much benefit typically. And secondly, it's sort of what I touched on already, using a linear model, you reduce the risk of overfitting the data, which is quite likely when you've got this imbalance between sample sizes and very high dimensional feature space. And it allows us to directly extract the weight vector as an image to give a sort of a predictive map that we can then visualize, and is quite sort of, to some extent we can think about interpreting it, but again we have to be careful, as I was saying earlier, about making local inferences. So there are many examples of kernel methods. I just listed some here that you may have heard of. Support vector machines, which are very popular and useful for classification. There are others, sort of Bayesian ones, such as Gaussian processes or relevance vector regression. And then again, more classical ones, once again, kernel ridge regression or kernel Fisher discriminant for classification. But there are many different methods. So one thing we can do with kernels, and has become quite and is quite popular in neuroimaging, is to use something called multiple kernel learning. Now, why do we want to use this? Well, in practice, we often have data sources from many different heterogeneous data sources. So this could be, for example, multimodal imaging. And we don't really want to just say the structural data on its own to do our classification. If we've got also diffusion weighted imaging, resting state FRI, for example, why not try to combine them all together? So we can do this with multiple kernel learning. But now we're not learning just with a single kernel, but with multiple kernels associated with the different sources of data. So multiple kernel learning has been proposed as an approach to do this, and what it does is it simultaneously learns a set of kernel weights, so how useful, in a sense, each modality is in the prediction function and the associated decision function in a supervised learning setting. So in MKL, you can consider the kernel to be a linear combination of a number of basis kernels. So here it's just expressed, K has been expressed as this sum over big M number of kernels. And it's a weighted sum. So this dm is essentially provides the weights for each of the corresponding kernels. And it's just a weighted sum, so the sum of these weights is 1, and each of them is greater than 0, or greater than or equal to 0. And then once you have this, you can then write the decision function for an MKL problem in this form, which is basically at the bottom, which is just the sum of decision functions over all of the different sources of data, all of the different kernels. So one example of an approach that's been used with SVMs is a simple MKL. So for the simple MKL, the weights can be expressed in this form here. So under the second bullet point, you can see how we express the weights for each kernel. And then what we do is that we simultaneously learn both these weights, the WM and the DM. We learn these simultaneously, where the DM represents the contribution of each kernel. So, as I said before, for example, each imaging modality to the model. And this allows us to write the predictive function as follows there. So this can be, it's simplified. So at the bottom there, what we've got is a sum of predictive functions, each one associated with each, for example, imaging modality, but it's a weighted sum over all of them. So just to sort of try and give more of an intuition of what this means, we can go back to our standard approach, which is just using a single kernel, for example, a single imaging modality. So here we would have a set of training data. We've extracted our features to get our feature vectors. We have our labels, and then we compute the kernel and estimate the weights. And this means that when we then have a new test subject at the bottom, we can once again extract its feature vector and then use the prediction function, apply it to this feature vector to give the prediction for the new test data. And then this just gives us our label. In multiple kernel learning, it's a bit more involved. So the example here is one where instead of each kernel being associated with a different imaging modality, each kernel is associated with a different region in the brain. So we're trying to learn sort of weights associated with each region in the brain rather than different imaging modalities. So here we're using the AAL atlas to provide the different regions, and we have this set of kernels. So each one is associated with a different region. So we have M regions. And we learn the kernel, K1 up to Km, associated with each of the regions. And these produce a set of weights. So this is the W1 up to Wm. So we then have a set of predictive functions associated with each region. When it comes to a test data point, in the bottom half of the slide, we extract, using our atlas, we extract the feature vectors associated with each region, and then we pass this through our model. So we have these models associated with each region, but we also have a set of weights, the D1 up to DM, that describe the contribution of each of the kernels to the overall model. So we can then use these and apply this to give our final label for the test data. Now, one thing that is very important is model evaluation. So how do we assess how well our model is doing? So ideally what we would do is that we'd have a set of training examples for which we learn the model, and we would have a different set of test examples for which we test the model. Unfortunately, we don't get, data is very hard to come by, and it's quite difficult. We wouldn't want to just split our data set down the middle into two different sets just to evaluate our model. We're likely to actually bias our performance to give probably an underestimate of the performance of the model because we haven't got as much training data. So what instead we'd use is we use cross-validation. So in cross-validation in the bottom half of the slide, what we do is that we sort of simulate train and test sets. So instead of separating the train and having one training set and one test set, we simulate within the same data set training and test set. So how do we do this? So here we've actually got an example of, I think, of leave one out cross-validation with 3 examples. So if we start off from the left underneath train test, we've got our 3 examples, S1 up to S3, And in the first fold, you would call it, you would train just using the first two subjects, S1 and S2, and test on the third subject, S3. On the second of the folds, we then swap things around so that we instead test on subject 2 and we train on the other two subjects instead. Then on the third fold, we swap things around once again and we train on S2 and S3 and test on S1. So the idea here is that we're sort of, without having to build separate training and test sets, we're sort of simulating different training and test sets, making sure that we're never training on the same subjects as we test on in the same fold, which is very, very important to be careful that you do that. Once you've done that, though, you then have test predictions for all of your subjects, and then you just can calculate error measures or accuracies in a sort of the obvious way. So if it's classification, be the number of correct examples divided by the total number of test examples. So here we have example of what's known as nested cross-validation. So this is something that you need to do if you're estimating what are called hyperparameters associated with the particular model that you want to use. So it's essentially the same as cross-validation, except there's another layer, so there's another set of loops you need to do, an inner set of loops, in order to do this. So if we start off with the outer loop, so in the outer loop you have, so on the left of the slide where it says split data, training and testing, you've split your data so that you want to test on subject number 1, and you're using the rest of the subjects for training. And then you go into your inner loop, and for the inner loop you need to estimate your hyperparameters, so you split that set of subjects from S2 to S5 in a similar sort of way you did for the original cross-validation, and you again leave one subject out each time from this set of data. So in the first fold you leave out subject 2, in the second subject 3, and so on. And we can do this and apply this and then evaluate classification accuracy over a number of different hyperparameter values. And once we've done that, we can then look at, for example, the mean accuracy across the inner folds in the table there, and just pick the hyperparameter that gives us the best accuracy. And once we have that, we can then use that to train the model in the outer loop. So the inner loop was just to work out what the best hyperparameters were, and then we can move on to the outer loop of cross-validation, which is what we're using to assess the model accuracy. So we could then do that, and then this gives us a prediction for that test subject. Of course, we then have to repeat this for all of our outer loops to give our cross-validation accuracy. So another point that's very important is that, okay, this gives us an accuracy, but how good is it? You know, if you're classifying two different groups, just between two different groups, you've got an accuracy of 57%. Well, it's better than 50%, so it's got to be significant, right? But of course, we can't really just rely on our intuition to establish how significant that would be. So there are different ways of looking at this. There's something called the parametric approach, where you would essentially set up a sort of a model. So often the binomial distribution is used for this, but it does have basic assumptions that are violated quite often in real data. So it's not very principled to use it. On the other hand, we can use what are called non-parametric tests, permutation tests. But these come at a very big computational cost. So very quickly, what these try to do is essentially break the relationship between the input features and the targets by using permutations and evaluating the model accuracy many times. And then we can use this to build the distribution of what the accuracies would be if there wasn't any relationship between, you know, the image features and the targets. And then we can see where our actual accuracy of 57% lies on this distribution. How likely were we to get it by chance? So this is a very nice way of doing things because you don't need to set up a model, but it comes at a computational cost because we would probably need to do, I mean, typically people like to do about 1,000 or 2,000 permutations, so this can be very costly. So I've got a couple of example applications to show you. So the first one is a neuroscience application. I think it's one of the earliest applications for machine learning to fMRI data. So this is from a paper from Mitchell 2004. There he was trying to discriminate between cognitive states at a given time interval, both within subjects and across subjects. So I think here that the task was that the subjects were looking at pictures or looking at sentences, and the classification task was to be able to tell, could you tell from the fMRI scan which they were doing. And if you look at the error rates here, for actually many different classifiers that he used, the error rates were always quite good, whichever classifier he used, so that's something that's quite nice. It shows some sort of stability. But yes, this is one of the sort of first applications of this sort of technique. The second example is a clinical application where the idea was to discriminate healthy adolescents at risk of mood disorders from low-risk ones. This is a paper from Yanina Morel-Miranda from 2012. So, yes, the idea was to discriminate between high-risk and low-risk subjects. And she applied, I think, a Gaussian process classifier and got essentially 75% accuracy for her results. But the interesting thing was that for the subjects who were at high risk, because the classifier actually gave probabilities, it gave probabilities of being at high risk or low risk. So looking at just those subjects, the probabilities were in some sense associated with the outcome. So the outcome after a few years, the clinical outcome. I can't remember the exact disorder, but they predicted that they were somehow associated with a clinical disorder that arose a few years after these scans were actually taken. So this was very interesting because it showed that it was actually useful for prognosis in the future, as well as differentiating between different groups at the baseline. So this is just a bit of sort of advertising for some posters from our group. So João has got this nice work that he's presenting, an oral presentation on Thursday and also a poster. So please come and listen to him talk and have a chat to him over his poster. It's using sparse partial least squares. I also have a poster about Gaussian processes, and Liana has a sort of a clinical poster looking at patterns of functional connectivity. So this is just a sort of a list of different toolboxes that you can use for neuroimaging. There are many available, and this isn't probably an exhaustive list. The last one, Pronto, is something that has sort of been working at the UCL and with lots of other collaborators. This is a sort of free tool. You need MATLAB for it, but all the other code is free, and you can use it to do many of the things that we've spoken about in this talk. These sort of kernel methods are all implemented there. So in summary, pattern recognition is a very useful approach for neuroimaging compared to the sort of the standard univariate ways of analyzing data. It can be much more sensitive to detect spatially distributed patterns. It also, we can use it to provide predictions at the single subject level, which is very, very useful. However, we do have to think about how we interpret these weight maps that are produced. I mean, they look nice and they give some sense of what's going on, but as I say, you can't really do local inference on these weight maps, so we have to bear that in mind. The other thing that we also always have to bear in mind for machine learning is to properly separate the train and test data. And that includes doing things like optimizing hyperparameters for for the models that we're using. We can't sort of optimize those using the test data at the same time, because it's not really very fair. You need to consider, when you're doing cross-validation, you need to treat the data really as if it's a training set and a test data set, and never use the test data set in any way during the training. So I'm just going to leave, I guess, this list of open research questions up here. I think they're all interesting, and it's sort of partly why this area of research is a very interesting one to be involved with, and a set of references. And that's it. So thank you very much.